a mechanism to have the Midwest schools bring in speakers from far away, California, East Coast, but share the expense. So the Midwest Mechanic Speaker tours around the Midwest and goes places like Notre Dame, Purdue, University of Michigan, etc. And the speaker is selected when these schools nominate someone in a Yale vote. So there are only four speakers per year, so this is considered to be very prestigious. Okay, so Professor Mark Meyers is a distinguished professor at UCSD, which is a high honor. He's a professor in the material science program in mechanical and aerospace engineering, and his general area of research is mechanical behavior of materials, which is near and dear to my heart. Specifically, he's studied a lot in dynamic behavior of materials, nanocrystalline materials, and biological materials. He's won numerous national and international awards, which are too many to list, but I will mention a couple. One is the Acta Materialia Materials and Society Award in 2010, and the Albert Sabor Award from ASM International. He's also a fellow of the American Physical Society and Material Society, OTMS. He's authored or co-authored over 350 journal articles, conference proceedings, and book chapters. And he has, additionally, written 3 fiction books, and one is on the table there. So these were one in 2001, one in 2006, and one in 2011. And I did look on Amazon, and the reviews look excellent. So they incorporate a lot of science in the book, so they look very, very interesting. And finally, the last thing I'll mention is that he was featured on Nova miniseries in February, I think it played, called Making Stuff. And so I think he's going to talk about today some of the things that were shown on that miniseries. So without further ado, Professor Meyers.
Thank you very much. I'm very happy to be here in the Midwest. I always loved the Midwest. Since a child, I've been coming here from Brazil. My parents would bring me to Goshen, Indiana, to visit my aunt there, and we would spend our summers in the Midwest. So what I knew about America was the Midwest. And then I came to learn the East and the West, which are just consequences of the Midwest, right? The center before the heart of America. So my talk today is going to be very, very brief. And I got into this field of biological materials like 10 years ago, 12 years ago. And so I'm still learning and I learned a lot here today with all the members of your department here. They each one brought 4 things that were fantastic, Amy and Brandon and all these spectacular new stuff. And so I think that the field is very young, so it's kind of in an exploratory stage. People are going in all directions, some wild, some very good, and some directions will lead to dead ends, some will lead to fantastic discoveries. And so I'll make the seminar very broad, so it's a mechanics seminar without the equations. I'm a little embarrassed that I think I have only 2 or 3 equations, that you have to be patient. You go to the individual papers, each of the topics can be treated at a quantitative way in a much greater depth, but I chose Brett. So I'll start that, and my co-workers here, my colleagues, Hoya Chen, who is at Tsinghua University in Taiwan, Joanna McKittrick, City Lim, International University of Singapore, Frank Talkie, and Eugene Olewski from San Diego. And I put some students down here, but we have many other students that also took part in this. And finally, the most important, we always put the National Science Foundation. Without their support, we would not exist. I looked at these wonderful campus and I see all these fantastic research. Without the funding agencies, this would all dwindle down to almost nothing. So, all right, so I like to start with this hexagon, which was a pentagon that Edward Arndt from Germany created, the material science hexagon. And what are the unique things to biological material science and biological mechanics are the following. All the things are set, and I am learning with you, so you shouldn't be scared by biology. Has thousands of different names. It's like geology. They pride themselves in giving names to everything that moves, crawls, or is just that. And we, in mechanical engineering, in material science, we don't care so much about the names, we care more about the concepts, the mechanisms. So don't be so scared with names. So self-assembly. Nature makes everything from the bottom up. It starts putting molecules together and assembles them. Whereas many of our processes are from the top down. We cast, we throw the metal into a large mold, and we cast a shape. So that's unique. Hydration, I cannot overemphasize, and I added this one to the arts pentagon. Hydration, all the biological materials, their properties are extremely dependent on hydration. If you dry, it's totally different. Depending on the hydration, their properties, all biological organisms exist within water. Water is what gives life. You know? Functionality, many of the tissues, many of the organs, they have more than one function. Nature has to take advantage and use something. The skin is a protection of the body and regulates moisture. The arteries and the veins, the bones, they all have more than one function. So whereas synthetic materials we usually design for one function. These are the lessons that we learn. And then hierarchy. The structure is hierarchical. All of the structures are hierarchical. Of course, metals are also hierarchical, but not to the same extent. The design is hierarchical, and there is a good reason for this, because the synthesis has approximately room temperature and 1 atmosphere pressure, so nature doesn't have at its disposal a large number of elements. It's calcium, phosphorus, oxygen, hydrogen, nitrogen, a few other ones. I don't know if you know, but silicon maybe, but it doesn't have tantalum, it doesn't have aluminum, it doesn't have vanadium or tungsten, high temperature materials. So, and then finally, evolution and environmental constraints, they determine the structure of many of these biological materials. Okay, so I'm going to start with a little bit of philosophizing, since I'm a fairly senior person with white hair. I always tell my students, don't philosophize, but I will do it, okay? All right, so in isolated systems, equilibrium is reached at maximum entropy. Then you study this in thermal. In closed systems, the equilibrium is minimization of free energy, like Gibbs or Helmholtz. However, in nature, we march, we go from, we don't have the equilibrium is actually complexity. The things are becoming more and more complex. And why do these things march towards greater complexity? There was a Prigozhin who was a Belgian, well actually his parents were Russian. He got the Nobel in 1977, and they reconciled thermodynamics with evolution. Thermodynamics of organic systems. That most organic systems are open, so they are not closed, they are not isolated, so they exchange matter with the environment, and you can create regions of order. And this was actually preceded by a Jesuit priest, Teilhard de Chardin, who wrote in his masterpiece, The Human Phenomenon, he wrote the law of complexity conscience, in which he approached the same phenomena, but from the point of view of philosophy. He was also an archaeologist. Okay? So we go from simpler to more complex structure, leading to greater order and self-organization. That's basically what we have in nature. Okay? And say, so basically, Prigozhin said that fluctuations can lead to self-organization, although the universe goes towards maximum entropy. There are open systems in which order increases with time. And this is he explained by his thermodynamics. And here I used a little bit of my writing that does, whereas the entire universe marches inexorably towards entropy maximization, I should put open systems evolved by self-organization and self-assumption and self-assembly towards greater order. So that's it, no more philosophy. But basically you have to understand that order in nature exists. You see, we march from minerals to organics, to life, to complex life, to organized life, to super life, to whatever, right? So biological materials and mechanics, as I see it, I mean, it's an evolving field, and it's comprised of biological materials. These are the natural materials. In England, they call them natural. These are all the materials that are used in biology. And I am not going to talk here about cells. The bodies and many organisms are composed of cells, and these are the little brains, the little robots throughout the entire body, and extracellular material that is basically often has a functional or a structural purpose. And we're going to stick with the extracellular material. Mechanobiology, this is kind of a new word, and there you go from molecules all the way to structures using the principles of mechanics, the beautiful laws of mechanics and methods that mechanics has developed. Then also biomaterials. These are synthetic materials used in biomedical applications. All these synthetics, joints, hip implants, heart implants, valve implants, stents, etc., in growing complexity, skin, etc. And then biomimetics, which is the area of bio-inspired materials and design. So in my opinion, this is what comprises this broad new field. And it's residing in the material sciences, it's residing in mechanics, and more people are involved in research on this, and I think there are going to be a lot of applications coming out of here. All right, so the basic characteristics of biological materials. Then, again, don't be scared by all the names. I look at this thing and it becomes simpler and simpler. Basically, most biological materials are composites. And they are composites, they have a soft component. For the most part, it's collagen. And then they have a hard component, and it's minerals. And it has there are a lot of other proteins too, other parts have intermediate filaments, etc., etc. This builds a large fraction of the biological material. So we have the molecular units, now the soft ones, the polymers, the soft polymers, they are basically we start with the amino acids, 20 amino acids, they form polymers, polypeptides, these are biopolymers, and polysaccharides. And then these ones form collagen, keratin, chitin, elastin, cellulose, and there are more of these things here. These are called the proteins. And the hard components, the minerals, are calcium carbonate, calcium phosphates, hydroxyapatite, and some silica, magnetite. There are 20 or 30 minerals, but these are the key players. These two are the 99% key. So basically, it's simple. Hard component, the minerals, they have a high compressive strength. The soft component, the biopolymers, high tensile strength. You put the two together, you have supposedly high compressive resistance, high tensile resistance. Depending on how they organize, you get isotropy and isotropy, just like in composite, where you put the different plies together with different orientations. We find examples in nature. Okay. All right, so I'm going to start with collagens. Some of you are very familiar with this. For some of you, it's something new. Basically, you have these amino acids that join together, they form a polypeptide chain. It's like we studied this in polymers very easy. In polymers, just like a polymer chain. Now, these three of these chains, they form a triple helix, and that's the collagen triple helix. Why do they form it? Because there are some of the bonds, some of these elements from the amino acid chains, they like to be together, they form bonds here, there's some good reason why this chain forms, this triple helix. Now comes the crux. These are 300 nanometer long. Don't ask me why they are 300 nanometer long. Then there is the head of this connects to the tail of this, okay? The head of this connects to the tail, the head connects to the tail. So they stagger like this. And then there's a little gap here. I don't know why there's a gap, but there is one. So if you add the gap and this overlap, and these two little things together, that is 67 nanometers. And why is it important? And I'll show you why. Because every time you take an SEM or TM picture of collagen, you see this here. And I don't know if you can see it, but you can see the little lines like this? And there, maybe it's a little too dark, but here. And these are 67 nanometers. There's 67 nanometers. And then I have some other ones that are much clearer. This is on bone or apple. Here you can see it. Can you see it? Yeah. And it's beautiful. You see it 67 nanometers. It's just like when you look at the structure of FCC iron, you see, or BCC iron, you see that characteristic. And this is collagen. And this is ever present. Bert Funk, Professor Y.C. Funk, who is kind of the father of biomechanics, he said, collagen is the steel of biological materials. So what does it mean by steel? Not that it is so strong, but it's present everywhere. In the skin, in the bone, in the muscle, everywhere, except when it's dead. When it's dead, it's keratin. Hair, everything, nail, hoofs, horns, these are all keratin. Feathers, all these dead things that grow out, and even beaks, keratin. So this one is beautiful. I like that. Can you guys see it? Yeah. Yeah. See? Look at that. You see these little worms, these are collagen fibrils. See the nice 67 nanometers. Now you understand. This is an SEM. This is done by a field emission microscopy. I mean, it leaves nothing to our imagination anymore. There you see. And it's beautiful fibers. Apparently you can destroy this too. Okay, and this was taken in honor of where's the big noise? Even the corn has the structure of a collagen. See, and it's a beautiful picture that we took. You see, nice. But I think there is some interplay with mineralization there. I don't think it's just the collagen. All right. So the structure of the presentation. I have roughly spent already 15 minutes, 20 minutes, so I need to get going, right? So I start with hierarchical structure. I'll give you some examples of hierarchical structures. Then I'm going to talk about structural biological materials. I'll give you 3 examples of structural biological materials. Then I'm going to look at some functional biological materials. And finally, I'm going to talk about some biomimetic applications, bio-inspired applications that already exist or that people are thinking. Okay? So, we have structural biological materials, functional biological materials, and biomimetics. All right, so let's start with hierarchical structure. And these are examples from our own research. This is the feather rachis. And the feather is comprised of its keratin and an external shell that is solid, and the internal foam, the cellular foam. So we look at this foam, and we look carefully at this foam, and we look carefully, it looks like this foam is solid, right? And if you look more carefully, you crank up the magnification, which we can do now. It's not solid at all. It's made out of the web, all these webs here. And these webs, so you have foam within a foam. So the hierarchy of foam. So you can make it so light, much lighter than if this was solid. And nature, the birds, of course, have to have very, very lightweight structures to fly. And this is how this is accomplished. Okay? The crab, this is a huge crab that exists in California, has the structure here. If you cut the shell of the crab, you'll find that, or lobster for that matter, okay? And these are, or lobster, okay? Arthropods, okay? That comes a word here, arthropods. Okay? And then you have these different layers, and each layer is composed of these fibrous bundles here. And they have one orientation. In the layer below, they're staggered. They're like this, like this, like this, like this, like this. So you can create with fibers, with these fibers, the totality is isotropic in the plane. And these are called Bully-Brown structures. They were first discovered by Bully-Brown. And then these bundles are composed of fibers, the fibers are fibrils, and then you have here you have little proteins and you have minerals, okay? And then so on, and then each one the chitin. The chitin they are not polypeptides, they are polysaccharides. And also the shell of many of these animals is composed of chitin. Okay, this is a huge fish in the Amazon. It's about 100 kilograms or more. It used to be 200 kilograms. It's composed of very large scales. The scales can be up to this big, extremely large scales. And the outside of the scales The outside of the scales is composed highly mineralized, hydroxyapatite, and the inside is a layer, is like layers of fibers in a plywood structure or in some bulldog structure. And each fiber is composed of 5 rows. So you see the hierarchy of this structure, leading to scales that are at the same time flexible and very strong. And I'm going to talk a little more about it later on. Okay, man comes here, how do we handle this? And Gao, Yuchan Gao, who is a very excellent scientist from Brown University, he created a mathematical formalism to address this hierarchy. And he basically, I call it the Russian doll, and he liked the word, so I put the red. And all these Russian dolls are identical, except for their little faces, and except the scale. Okay? The scale, one fits into the other. The same way he had this, he has exactly this, level 1, level 2, level 3, level 4. So one fits within the other, fits within the other, fits within the other. So it's kind of a, what do you call it? He applied mathematics to it and came up with equations that describe the mechanical properties at this level, and as you go up. And what happens essentially in the summary, what happens is that you go up at this scale here. The strength is lower, but the toughness is higher. So you lose in strength as you go up here, but you gain in toughness. The ability to arrest cracks is increased here, and here it's practically 0. And this is very important. Nature uses this because nature is dealing with very weak materials, so it's not. So basically, as the hierarchical level increases here, the strength goes down, but the toughness goes up. So you reach a level where you have both strength and toughness. So these types of interplays are very common in biological materials. And so this idea of Huijang Gao to look at it and systematize it led us to look at Abalone and we define the number of hierarchical levels here. So we found 5. Apparently for bone there are 7 hierarchical levels, and you have to look with bone all the way from the nano level to the structure level, and the structure keeps changing and these things keep working together. So I'm going to talk about this in a little while. Okay, so now structural biological materials. I'm going to give you, we studied, we went on a rampage when we started on this, and there was nothing that we didn't study, you see. And our curiosity was boundless. So we looked at the number of conches, clams, abalone. We started with abalone, then we looked at arthropods, started carp, horseshoe crab. Horseshoe crab is totally different from crab. Teeth and tusks, piranhas, all kinds, sponge spicules, armadillo. And then we keep finding other materials whose this is kind of exploration. I said it's like Christopher Columbus who came to America. He would go from one island to another island, another island. He didn't stick with the first island he discovered. So I'm gonna describe abalone, bird beaks, and fish scales. And I'm gonna have abalone as a structural material and also abalone as a functional material. Okay? So let's there, and I'm going to start with toucans. And I'm going to pass the toucan here. This is the toucan beak, and this is beautiful. And the reason I studied this, you can see me on TV, you see. And it's true, I was a teenager, my father was hunting, and I was laying there in the forest, bored. Toucans were flying over my head, and I saw the skeleton of a toucan, and then I lifted the beak, and I said, this is so light, so extremely light. I was so stupid, right? And but yet fairly strong. And of course, it has to be very light because the toucan would go on a nosedive if it was had a beak. So it has to be very light. Wait, and I think don't twist it too hard. Just look at it, okay? And this is due to the fact that it has a sandwich structure. It has a sandwich structure here. The outside is keratin. Keratin, very soft keratin. So this is the outside, the keratin. You see, I'll pass these around too. Soft keratin. And the inside is a very lightweight, very porous bone here. And the core has nothing. The core is hollow. And there's apparently some vascularization and stuff like that, but I don't really know about it. The thing is that if it breaks, the toucan is in bad shape. And it uses this beautiful beak to forage for food in the tops of the trees and in fencing activities, so the boys do that to get the girls. And also, since it's now, this week is what, Halloween, so I'm going to tell you a horror story about this beautiful animal. He goes into the nests of little birds in the tree trunks. There are holes, he goes in there and he takes little babies and devours them. He's only good looking, but the nastiest position. So the hornbill, the same way, also has its head, but it is heavier. Here you have the density is about 0.1 gram per cubic centimeter. It is very light. So it's about 1/30th, 1/40th of the weight, but 1/3 of the total length. So it is a material that aerospace engineers look at and say, aha, I wish I could design as well as this. Okay. So we did CT tomography on this, and you see inside, you can see that, I'll show you here, you see all these struts, all these bony struts here. There's a very thin bony shell, and then we took these little pieces, we tested them in compression, we tested them in tension, and these are little oil buckling loads, and then between these struts here, there are actually membranes, there are thin membranes, so it's a closed cell structure. And these thin membranes play a role, and an important role. And if there were no membranes, it would not be such a deal, but it has a closed structure. So this CT is transformed by volume rendering, and we do it into a finite elements. And I don't know if this will work in this computer here, but no, it's not going to work because we were able to model the compression of this, and we can look at how this structure collapses and follows. We also can now model the entire structure of this here. And again, I'm not going to be able to show you this movie because it's not connected. But this essentially collapses and undergoes buckling, and we compare the loads. We can compare the loads. This is displacement times force of the entire beak experimentally observed, and then this is what we observed is about 1 millimeter thickness shell with it, which is more or less what is observed. So we get a good match. And the reason we did that is because we were approached by a Brazilian professor that was manufacturing, for the zoo, he was manufacturing prosthesis for toucans that had lost the beak. And to compare the natural beak with the beak that was a prosthesis, and the prosthesis were much, much weaker than the natural beak. Okay? So now, we applied the Karam and Gibson, Lorna Gibson analysis that she applied, she developed, and she did this for plant stems which have this shape. So we basically transformed our toucan into a cylindrical beak, and we put the foam here and the shell outside, and we looked at what is the effect of creating the foam rather than putting all of the bone outside. And the bending strength, as it happens, the fact that you use this sandwich structure with this foam enhances the bending resistance significantly. The bending resistance is significant. Now these are the maximum bending moment, 10 to the 0, this is equal to 1, and this is the reference point. So as you have these, as you increase the radius, the thickness of the shell here, ratio to the radius, as you increase it, you get an improved performance over one. Okay, so there are definite advantages, and okay, so basically this bending moment is increased significantly. And that's why the toucan beak has this. The reason it does not, it's hollow in the inside is that we know that in bending, the bending stresses are very small here, because the bending stresses, they vary with distance. So since the bending stresses are small, there's no need for any material, so you save a lot of material by putting the foam on the outside. All right, so the abalone shell. The abalone, I have the abalone here. Before I go to the abalone, And this is the example here. This shows, this is just an illustration saying that if you just have the foam by itself is very brittle, it breaks. And but if we put this, if you put it on, this is very also. But if you put the two together, you get a structure that is a synergy. There's a definite synergy in the structure, which we calculate the two and we measure. And so there's clearly a synergy in this the structure of this of the two atoms. I also have a cast here. I have this one. It's not so nice. There's no comparison with the. It's not no means as nice as the toucan, the hornbill, but the same principles of it. And here is the abalone shell. This is a very beautiful one. It's supposed to be very tough. Unfortunately, it was polished almost no thickness, so it was polished down. But the abalone shell is comprised of about layers of calcium carbonate, and these are organic here. This is organic. Now these are about 0.3 millimeters. So but if you look into the calcium carbonate, it's not the solid calcium carbonate. This calcium carbonate here is comprised of small tiles, okay? And these small tiles are about half a micrometer thick by about 8 to 10 micrometers in diameter. And they are separated by tiny layers, 20 to 30 nanometer organic layers. And here we have these chitin molecules. I'll show them later on. So basically, this is the hierarchical structure here. And this material has properties that are significantly better than pure calcium carbonate. This here is calcium carbonate. This is chalk. And if I hope that if I have the strength there, I can break it. See? But I cannot do the same thing to abalone. Okay? All right, so here is, if you look at the growth, so we looked at two aspects. How do these things grow, and what are the mechanical properties? I'll first talk about the growth. If you look here, these are the organic layers here. It's kind of dried out and cracked because in the SEM, these very thin organic layers crack. Here there are the layers folded, and then on top we have a little bit of a Christmas tree that is seen much clearer here. If you look here, you see one of these terrace cones. So we have the various layers here, and the growth proceeds in this way here. This is how the growth surface looks like. If you look in the SEM, okay, that's what you see. And the growth here, these tiny ones, and then between each one there is going to be an organic layer. And I'm going to show you how the bonding, what kind of bonding we have between these different layers. The bonding is actually in this direction. If you pull it in tension here, we were the first to test it in tension. It's very, very low strength. It has very high strength in tension in this direction. Compressive strength is high, but in this direction, surprisingly, very, very low. But you don't need strength in that direction. See? There, okay, there. And this is AFM showing again. Here you see the little growth, terrace cones. This should be nanometers. So each one little step here, this is a profilometer, little step, 500 nanometers, 500 nanometers here. Okay, so these are about 500 nanometer thick, each little step. And there's a reason why they are 500 nanometers. They are not always 500 nanometers. Like I got some shells from the Arapaima River. There they are about twice as much, but in here they are 500. So how do the growth take place? This is the C growth direction. The orthorhombic direction of growth is this here. So this is a fast growth direction. But the animal lays periodically this organic layer which slows down the growth and will enable the growth to take place here, and then eventually it grows through air. Here, this membrane is semi-permeable, meaning that the ions can go through it and go to this side and those side. Okay? And then again, it lays down the second step, and then here this grows and this grows. So this grows, you can see how it finally makes its way through here, and then they grow and grow, and this is growing, and when this one becomes of about 0.5 micron thick, the animal puts the fourth layer here, and put another layer, and then the same process repeats itself. So you then construct these growth cones. Okay? Now, the thing is, what is interesting is that the crystallographic orientation, here, they're all the same crystallographic orientation. So and there are small bridges between these layers Angela Belcher in the 1990s at Santa Barbara. Okay? And we also did TM, so we find this, they all have the same crystallographic orientation, so it's a pseudo crystal. It's just pseudo, it's not an epitaxial, it's like an epitaxial growth. All right, so how does the animal regulate this? And this is our idea. The animal has here, that's the epithelium, and it has some cavernous bodies here, some holes here, which you see here and here. And inside the hole, if you look carefully, you see tiny little chitin fibers. It's not clear, but and then it kind of injects or extracts these chitin fibers, and then they form this layer, and this kind of stops the growth. So the animal grows these things, and then that's the crystal grows at the layers, another level. It's like a mason puts the bricks and puts the masons, puts the bricks, puts the masons. See, that's how the animal grows. And if there is a time in which there is not much food, the growth stops completely. All right, so this is the organic layer here. It's all these chitin fibers that we see here, and it's a network of chitin fibers. And then connecting to here, there's some aspartic acid. There are people that have identified other amino acids, but we did not look at the details. Okay, so the importance is the strength. The compressive strength is about 400 or 200 megapascals. Okay? What differentiates this from ceramics is that the tensile strength is actually fairly high. It's about, so the ratio between the two is about 1.3 to 3. I know, for instance, that this I was able to break, but if I put two of these here, I'll try to demonstrate this problem in work, but if I put my foot here, it can take my weight, you see? So that was almost. So the compressive strength 10 times higher than the tensile strength. Here's 1.3 to 3. That's the whole idea. There. So this is why they're tough. Now let's look exactly what happened. As I said, we tested this in tension, and we got a strength of 3 megapascals. Very low, extremely low megapascal when you pull like this. So there are only a few little bridges here. When you do compression, you get about 400 megapascals. So you gain in one direction, you lose in the other direction. You're not really gaining anything. So these little bridges are shown here. You see little bridges, and here you have a lot of bumps, and these are called asperities, the bumps. And a few of these bumps, they form bridges from one layer to the other. And these little bumps, they are also actually was proposed by Evans and one, that these are toughness mechanisms. But we think that these bridges are the main. Okay? And here you have the organic. This is the organic here. That organic is kind of dried out. Here we got rid of the organic. We dissolved the organic away. That here you have the organic still present. And here are all these little bumps and bridges. Now, some and all in they did this study, and also Shepard. They did this study, and they found that there are about 35 to 45 bridges per time. And here I go back to Hugh Gao in PNAS 2003. We all know this equation for fracture toughness, K1C. If you just put it expresses the fracture stress is K1C divided square root of pi A, which is the flaw. And if you take the dimension of the bridge as exactly equal to A, or 2A, if we go, as the bridge becomes smaller and smaller and smaller, the maximum strength would rise according to here. But this is the theoretical tensile strength of calcium carbonate. E over 30, you get approximately here. So these two curves, they will intersect at about 56 nanometers. And this is approximately the dimension of this little bridge. These bridges are about 50 nanometers thick. So nature has reduced the little bridges to the size where they cannot get any stronger. So if we now go to calculations, we know that the tensile strength with 3 megapascals, we know the strength of each bridge would be about 3 gigapascals, and we have we multiply the strength by this by the area here. We can then calculate how many bridges we would need to get 3 megapascals. And we go through it, we get 36 bridges. And song and now they found that it's between 35 and 45 bridges. So if you look at all these bumps here, only 1 in 10 or 1 in 20 will be a bridge. The other ones are just bumps. Okay? So, why is that? Well, because if these tiles are if these tiles are bonded too strong of a way, then they will not fracture, they will not pull out like this. And there is the same thing in composites. If the composites are too well bonded, they will break by a normal fracture. If you don't want that, you want the composites to break by fiber pull-out. When you pull the fiber, the energy you take to pull out the fibers, that is good. And so we have this. And I'll show you here, we can kind of calculate here the strength, the shear strength. We can go to the thing, and we get shear stress of about 10 megapascals if we calculate. So we can, everything kind of fits together. All right, so we basically have 3 mechanisms. Asperities, you have this organic glue, which I don't think is that important, and then you have the bridges. And if you add the 3 things together, that's why Ivana asked me, why are they so tough? So this is, I believe, that maybe it's much more complicated than that, but that's as far as I see. Asperity is an organic glue and mineral bridges. You can calculate the shear stress of these bridges, and we know how many bridges we have. Okay, so now to the Arapaima. Unfortunately, I don't have any Arapaima scales to give you. And I ran out of them, we have only a few. But I was in the Amazon and I see this beautiful animal here, that's not me, you never see them. But they live in lakes, and they actually come out and breathe every now and then. They're so primitive, they have lungs. And they live in lakes that have very little oxygen. They come out every 20 minutes. That's their down. That's their lip. And the Indians wait for the arrow. And but they have these big scales, and we ask ourselves why? Well, these lakes are infested with piranhas. They are full of piranhas. Anything that falls in the lake is eaten readily, except these things. And why? Because they wanted to show that these scales can resist the piranhas. So I showed you this already. So we look at the mineralization. The outside is highly mineralized. The inside is much less. So this calcium, hydroxyapatite is barely visible. And these are the layers here. There are lots of cracks, and these cracks are produced when the material, when the scales dry, because they dry by shrinkage. Okay? And these layers are, it's not 90 degrees, it's like 75 degrees, 70 degrees from each other. And the outside has this serrated, this corrugated structure that is highly mineralized. The hardness is like 200 megapascal, and inside it increases to 600, 500, 600 in the outside. Okay. So, and you see all these cracks. If you actually, I was able to kind of guess an angle just from the pattern of cracks. But there's a 1, 2, 3, 4, 5. If you go, every third layer has, they are like this. They keep that. You see, they are parallel to this. Parallel. Here they are parallel. So these are the fibers. Again, collagen fibers at different orientations producing the strength. See, and this is about 75 degrees C approximately. Okay? 60 to 70 degrees C. Okay? And these are the fibers. And these fibers, when you pull the material apart, they break, they pull, they tear. You see, and that's what gives the toughness. Now I'm going to show how hydration is so important. These are the wet scales. These are the dry scales. The dry scales have a stress of about 50 megapascals. The wet scales about 20 to 30. Now these ones here have if you take the area here is higher than the area here, so the toughness is higher here. Now they undergo what's called graceful failure. These little notches here correspond to initiation, when it starts cracking, but it doesn't break. It's graceful failure, you see. It doesn't break right at this level. It keeps going, the blows keeps going. So then I had the moment of inspiration. I needed to get the paper accepted, so I said, why? He said, why are you studying this? And I said, I need to come up with a good reason. So I said, this is a flexible stick And then the bottom is comprised of a polymer that is much more ductile. So we could actually bend the ceramic and have a braided structure here. And why would it be corrugated? And the reason I thought corrugations are good is because they decrease the overall stresses. If you have this stick like this, the stresses up here are higher than the stresses, much higher than the stresses here. Because this here shows you, we went to equivalent heat analysis and showed that the stresses are much lower here, but not that much lower, like 20%. Okay, so here is the enemy, the piranha. So here are the teeth, very sharp, about 45 degrees, and sharp cuttings, and they act by they have the way they act by the guillotine action. So they slice through the epidermis, through muscle, and very, very easily, and we apply the pressure and squeeze the epidermis and the muscle in here, okay? And what we did, I have to show you this. This is not the piranha. This is the great white shark. And we looked at this, I looked at the picture of the teeth of the great white shark. These are the serrations. This thing can slice through meat like a rabbit through lettuce. And it has a shape that I remember from my high school days, a curve called the cycloid. And I don't know if you're familiar with the cycloid. You study it sometimes in mathematics. And I always like the cycloid. But basically, you have to draw it. And then you have a circle, you have a point on the circle. When you roll this point on the circle, it describes a trajectory plus this. So I thought this is cycloid. So it is pretty close. Now why? That's another question. I'm doing some work on this. I don't want to talk about this, but that's some later. If you invite me again another 10 years, I'll And the piranha, here's the piranha, has, again, just like us, it has an enameloid structure on the surface, high hardness, and the core is much lower hardness. Nature, again, chooses this often, puts a surface that is very high, very hard, and the core that is soft. And this happens in many species. So it's called evolutionary conversion. We have not much to do, we don't have much evolutionary in common with the piranha, except for our adaptation, appetite. So here they're not very hard, very soft. So I said, is the piranha going to cut? And these are the teeth, these are the muscles, we calculate the muscles. I came up with this force, which again is questionable, but it's the first approximation. Okay? So we looked and we took the piranha tooth, one piranha tooth, indent the scale. And under the scale we put some rubber. Go in, go in, go in, go in, and then pull out. And lo and behold, when you pull out, this tooth breaks. You cannot take it. Friction holds it up and it breaks the tension. So if you look here, and this one breaks here, this one breaks there, and then these other ones, when you remove the load, they break. So here is the result. That's the explanation why the piranha and the Arapaimas are good friends. They live in peace and harmony. Okay? So there's another fish, and this is a fantastic fish. I just started studying. I have here, I got from a lady called Diane Ellery from Mississippi or Missouri. If you want to buy a gift for your girlfriend, if you want some alligator guard jewelry, she makes alligator guard jewelry. And she gave me something, and so I wear it until the project is finished. And this looks just like a, it looks like amazing. People tell me it's a tooth. It's not a tooth, it's an alligator guard. And small people wear it for their dances. So here it is, and it's covered, it's bone, and then it's covered with ganoine, which is very hard enamel. And this fish goes up to, it really becomes enormous. This fish is up to 10, I've seen pictures, 10, 12 feet, this fish, enormous. So this fish is completely armored. See, nothing can get through it, see. And this bone here, that's bone that has hydroxyapatite, and we are now taking pictures, we are looking, again, the structure is not exactly the same as ours, it's quite different. And the collagen is not like this, the collagen is aligned like this, in different fibers, and with the mineralization and in between. Okay? And the ganoline is very, very high hardness. And okay, there's also a lady in MIT, Christina Ortiz, she studied another one called Senegalensis. It's a very small fish that is on. And this is the only reason I can see it's armored like that. It's probably against alligators. It has protection against alligators. That's the only reason I can think of. And I promised Diana earlier that I'm going to go to Mississippi this year, and I'm going to go and spearfish one of these. All right. Functional. Biological materials. I have still a few minutes left. I'm always running behind. This is the gecko of our good friend, the gecko. The gecko has these fantastic attachment devices here. And these are little microfibrils that are nanoscale fibrils, millions of them, each one with the van der Waals forces that attach to surfaces. Okay? And there is a scaling law that if the animal is small, the attachments can be bigger, and the bigger the animal, it didn't have to be the attachment. I'm not going to talk about this. Many people are studying. I'm going to talk about something else. This is the abalone foot. That's the snail. And it sticks to walls with great desperation because of the sea otters that want to pry it out. And these are the waves that form. And then if we look carefully, and if we look more carefully, we see these little wiggles, like little wormies here. And these are fibrils. Can you see them here? Nanoscale fibrils. It's filled with nanoscale fibrils. And what we think is that they play a role in the attachment. So we took the abalone here. This is the graduate student Albert Lynn, who now works for National Geographic. You can probably see it on TV. And we pry these things out of the wall. And we take enormous forces to pull these things out. You take forces, you cannot do it by naked hand. This is why the predators cannot get them. And we feel that we look at this force, we calculated the stress, we looked at our engineering, and I'm not going to go into the details, but here we have tiny little these fibrils. We put them in the AFM, we go, compress, and then pull in tension, and then it breaks apart here. We can calculate the on the force required. Like here, you approach the surface, it touches van der Waals forces, you pull, you push a little bit, and then you pull, and then when it comes apart, then you measure this force. You calculate this, apply an equation called Johnson, Kendall, and Roberts. These guys, these fellows from Cambridge, they look at the van der Waals forces when you have a semi-spherical cap on the free surface. They came up with this equation. Beautiful equation, and we find that each setter has a force of 300 nanonewtons. Okay? And then we crank out, and then we calculate the total stress per abalone is about 123 kilopascals. And that's very close to the measured value of 110. So this could explain it. However, basically what I think is that these nanofibers, they close all the gaps, and they conform very closely to the pebble foot, so the water cannot get in. If the water cannot get in, then you have what's called acting, you have the forces of the hydrostatic pressure that you have to overcome. The force has to be equal to the hydrostatic pressure, and it can conform to many students. Okay, the other one, I'm not going to say much about this one. This is a tree frog, has also pads, very soft pads. It sticks to the walls beautifully, to the side walls. And what is the mechanism? Well, Barnes, John Barnes from England, studied that these are little hexagons, and he said that there's a fluid here in the hexagons in between, so it squirts out this fluid, and that creates the suction effect. But we look carefully at these pads, and what do we see? We look here, and we see something almost like a little suction caps, nanoscale suction caps. Yeah, it's almost like fibers. So this could be playing a role. That's what just we need to do more than just after 20 minutes. Part 4, and I have about 10 minutes for part 4, and then I'll close. That's biomimetics. That's where engineers want to go. See, they want to apply these principles to find new applications. And so there are two ways of approaching it. One is the traditional biomimetics, and this has been always since Icarus. He made feathers. His father made him wings from the bird feathers and stuck wax, and he flew, but then he dropped dead because wax now. But there's a guy in Georgia, there was, in the 50s, he created Velcro, the lure for sheep. And this was a tremendous success. What we are moving now towards is the molecular-based biomimetics, bioduplication, new methodologies, genetic engineering, and everything we are using, we are working with nature and using the methodology of nature to reproduce nature. And efforts are going on here already. Okay? So these are the birds that George Mistral saw. He was hunting with his dog. The bird stuck to his coat, and when he looked carefully, and these were the little hooks that he saw in the birds. And then he had the stroke of genius and said, aha, I'm going to use this for Velcro. I'm going to create Velcro. So it took him 10 years to create these little loops with collars. 10 years, and you see that these loops, he created one loop, probably cut, one loop, cut. So then you create these loops. And then the other side is only, these are the little hooks, and the other side are the loops. This maybe can be used, some of the principles, but we also took zirconium nitride, PLMA made like sputtering, we made these things here. But this doesn't really work very well. It takes forever, and it makes things about tiny, and nature is much works, does it much better and much faster. So here I'm going to show you what works. Tom C.R. Ritchie and Alvin Sayers, they did freeze casting. That's a fantastic technique, freeze casting. This is a slurry of aluminum. They produced these ice crystals here. Then they took it and they dried and freeze-dried this thing. And then they get holes created. They take this, they sinter it, so that this is all solid. And after these channels are built, and then infiltrate whatever, PLMA, polymers, the aluminum, and then you create a structure that somewhat resembles the So here are some lamella structures. That the brick and mortar concept is actually important too. It's not just layers, but the layers have to be short. They have to deliver the tiles. Tiles are better than layers. Okay? And then you have the fracture, the crack extension here, and this is the toughness. So if you look here, this is aluminum. A toughness of about 3 megapascals per square meter. And all ceramics except zirconium, right, have this poor toughness. That's why we move towards composites. Nacre goes like this. Nacre starts slow, but nacre you see that it increases as the crack increases. And that's what our curve behavior. And that's the desirable thing. There's extrinsic and intrinsic toughening mechanism operating in nacre. So nacre is bigger than aluminum. And then the bigger one is the brick and mortar alumina PMMA composite made by Ritchie and Tomsia. It went up to 30 megapascals per millimeter. That's fantastic. That is no other ceramic. They have 95% aluminum. No other aluminum composite can reach this. So this is, I think, one of the top. Now, can we produce this in industrial scale? Can we expand this technology? I don't know. And this is the whole fact. We have to look into the future. We are doing research not for today, not for tomorrow, but 50 years from now. I think 50 years from now, there will be fantastic things. People are working on things nowadays that people look, that's never going to work. And being one day it will work. Okay? So, these guys in Germany, Arts and Huber, they do these artificial little pillars, of silicon. And they can vary the size of the pillars. And if you go from a large pillar to small pillars, then the force, the pull-out strength increases. So this is like 10 kilopascals, where the large ones, from 1 all the way to 10 kilopascals, are reducing the size of the pillars. Also, they change, these are cylindrical pillars, and by making little mushrooms here, they get improved performance. These little mushrooms are better. Okay? So people are already coming up with reversible attachment devices that have engineering application. There is some professor of engineering came to me with an application. I cannot discuss it here. It's secret, but it's hilarious. If I told you, you would laugh like crazy. But he got me in touch with this professor, and they needed some of this stuff. And I'll tell you later. But then this is the P4 phage. And this is just to give you an idea, that's a phage that is a virus. This is a tremendous animal. It does not need a reproductive system. It injects the DNA into the cells. That's the cell freedom, like a cuckoo. And then creates millions of other little phages. They destroy the cell and move on. Okay? That animal, or whatever it is so tremendous that we break it apart and it assembles itself. See, it's so primitive that it can reassemble itself. And that's a scary thing, but people are using these phages and combining this with molecules and creating batteries and creating things that will come to harm us in the future. Right? They attach to these phages, they attach all kinds of molecules, and then they are using them and combining them and mounting them together in assemblies. And these then are Angela Belcher at MIT is doing this. It's fantastic and creating batteries that have much higher performance. Okay? And I think this, I'm going to go then to the conclusions, that nature has at its disposal a very limited number of materials and processing methods. We have much more, but what nature has is the ingenuity. Okay? So if we understand the structure, property relations in nature, we can create things that are perhaps much better than the natural system. Okay? And then we apply the methodology to biological materials. Okay? And we seek to create new materials and structures inspired by nature. As I see in the future, I put material science, but I should put materials and mechanics. Right? We'll be at the confluence of biology, physics, chemistry, and since it's mechanics, I should put mathematics. Right? Put the 4, and then this would be the future of biological materials. And the last, but not least, I wrote the books of musical Meyers, and I don't have copies of you, but I recommend that you should. It's a novel that incorporates science, fiction, academic intrigue, and biological materials. And then here is the one that I have, the Chechen Jihad, and I have some copies here. You're welcome to, I'll sign it for you. Tell your friends to buy one if you get tired of your research. It's also an explosive that was discovered in New Mexico, and it's 1,000 times more powerful than conventional explosive because of some biological processes happening in this explosive. Thank you very much. I forgot to show this. And this is how this thing works. This is how the tiles work. See, this is why this material is so strong. Okay, when you pull it apart, you see that gives it the strength. Okay? And the dimensions are small, so the cracks are small. You don't have big cracks. Okay, thank you very much, and it was a great pleasure. Yes.
Comparison of piranha and shark. Which one is sharper?
The shark. Okay, the shark has a powerful bite. The piranha, you see, that's a good question, and I'm actually studying this. It's very, very good. I'll tell you, the great white has these serrated teeth. And the piranha has tiny serrations, but all the fish that eat other fish have sharp teeth. They don't have serrations. So the serrations are there. There are serrations in nature, and they are what's called evolutionary. Tyrannosaurus rex has serrated teeth. Yeah. The Komodo dragon has serrated teeth. There are some alligators that have serrated teeth, some primitive, some prehistoric alligators. So the called megamouth, the big shark, what do you call the enormous shark, prehistoric shark, megamouth, right? Like a human shark. Huh? It's a shark that was the size of his room, a prehistoric shark. It has teeth this big. It has serrated teeth. Now the serrations are there because they slice through the skin of mammals. So when you bite into fish, you don't need serrations. You just go in. So, and I'm studying this, and so I would say that the great white is much more designed to slice through humans than the piranha. That is meat seals. Seals, humans.
Well, maybe on that